for the very warm welcome. Okay, hello, thank you everyone, and thanks for the very warm welcome. I'm very honored and excited to be here and to introduce some of the things I had the pleasure to work on. I will make this a brief introduction into one of the things that I think are interesting and relevant to your work too. I've been following especially Dr. Wobson's work. So it's very, very exciting again to be here. And thanks for the invitation. What we'll talk about today is one piece of work that was recently published under the name Geometry, Information, Duality, and the quantum entanglement contributions to gravitational dynamics. So his work is part of a broader effort, a corpus of work that tries to bring quantum information and general relativity closer together. This specific piece I'm talking about today, I did myself, but there are many other pieces connected to that where I have collaborators and contributors. So this is really a joint effort between uh, many people, not just one thing that I've been working on in the past. So the core idea of this thesis that we'll talk about today is the introduction of an informational stress energy tensor that is derived from the entanglement entropy of quantum fields in curved spacetime. And this tensor supplements the classical energy momentum tensor in Einstein's equation and encodes the contributions of information, specifically from entanglement across spatial regions. And my goal today is accessibility. So there's always more to say, there's always more to discuss, and we'll have the chance to talk at the end. So in the presentation, you will not see any page-long tensors. And a few equations will appear, but these are genuine and they're all published. And for the roadmap today, we have basically a motivation that we start off with. So two motivational slides talking about the black hole entropy law and the data deluge stack that we'll briefly talk about of hard drives. So it's a metaphor, but I hope it serves the purpose here. And the goal is really to get out with the key message that information gravitates. And then we'll move on from entropy to curvature, and we have a conceptual backbone here. The conceptual backbone is we start out with Heisenberg, with quantum uncertainty, which gives rise to entropy, and then we move on to curvature. So entropy leads us to curvature. So we have a quantifiable measure then of what's not determined, the quantifiable measure of entropy. And once entropy flows, it becomes structured in space, it carries energy momentum, and that gives us the curvature. So that's what we will talk about in more detail. And lastly, we'll have observational windows. So we'll talk about the potential experiments that we will expect in the future that will help us to verify that idea, these thoughts, and see if we can gain some insights, for example, from the next generation Event Horizon telescope, where people will image photon rings of Messier 87 star and Sagittarius A star with less than 10 micro seconds accuracy, which should be enough to detect a fractional change in ring diameter predicted by the informational coupling that we will discuss today. And the gravitational wave dispersion experiments, LISA, those will be relevant examples too. And then lastly, we'll conclude with broader connections and an outlook on holography, thermodynamics of computation, and tests that we can do and expect up until the 2030s. Now, the first question is, why would we care at all? So, and why would we start out generally asking that question if information gravitates? So let's start with the most extreme laboratory that we all know very well. So I know I have a very educated audience here, so I will not go into much detail, but it's the black hole. So in the Bekenstein-Hawking formula, which we see here in the slides, that already tells us that a black hole is entropy is proportional to the surface area A and not the volume hidden behind the event horizon, which is generally, so if we start out with thermodynamics, a very interesting thing, because in thermodynamics, we learn that entropy is an extensive property you double a system in volume, you double the entropy. And black holes break that intuition. So it is of all the microscopic degrees of freedom that we have live on the two-dimensional event horizon, which is also what gave rise to or is a hint of the later holographic principle. And the figure, I don't think we need much explanation, but so the figure shows space-time in the usual image that we all know, stretched over a rubber sheet, and we have latitude longitude grid that presents the coordinate mesh, and the event horizon is the black disk that we see in that figure, and the mass collapses the grid inward and creates the curvature as we know it. But what we start out with as basic motivation and as key message from this first slide is that entropy already carries geometric weight. So the area law is basically geometry speaking in entropy units. And information refuses to stay in its box. So that means Hawking radiation suggests information may leak, but the information loss paradox arises because geometry and information insist on being in the same regime, playing in the same sandbox, so to say. So these two facts already give us sort of a license to promote information to a source term, a bona fide source term in Einstein's equations, which should, if correct, stand on equal footing with mass and standard energy. Now, if we move on with the analogy that I briefly mentioned before, and it's really just an analogy, but I hope it serves the purpose. So we zoom out a little here from the black holes to something much more humbler, hard drives, or generally storage media. And if we think about humanity's data production and how data is stored. So only the last year we wrote about, if the number is correct, about 10 to the 24 new bits. And on the left bottom hand side, as you know, we see Shannon entropy, which says the entropy of one single bit contributes to that, which is the Boltzmann's constant with a natural log times 2 for two possible states of a bit. Now, if we take that and multiply it by yottabytes, the magnitude of 10 to the 24, and then exceed the entropy bound of the Milky Way's baryons, which is not an exaggeration, but is really that number that already should give us some further thinking. It matters because on the right bottom, we see Landauer's principle. It says we have a thermodynamic price tag anytime we do erasure. So, and that means if deleting a bit costs us energy, one of the next questions one may ask is, does the entropy of one classical bit also source a tiny piece of curvature? So in the geometry information duality, coming now closer to the core of that thinking, says yes, and the hard drive stack in the figure, as we see, is bending the rubber grid, very much like the black hole, but this hugely exaggerated. So it's just a metaphorical purpose. So asking the question, does the bit erasure source curvature, is simply asking the same logic. If entropy flow gravitates, then even a quantum of energy, entropy, sorry, associated with one bit should gravitate. On a very small scale, but it should. So, and the bigger we become, the more extreme the regimes become, the more important and relevant this will become. And now that's the basic motivation that we have. So we just throw out that statement, every bit must gravitate if we want a generally universal storage or bookkeeping of entropy. And the next step would then be to formalize this entropy, uncertainty entropy curvature chain. So moving on now to this transitive chain that we see, we see the left-hand side, the Heisenberg uncertainty, which tells us how accurately we can measure, for example, position and momentum of a system. It doesn't apply only to that, as we know, but starting out with this one, we say it can be sharpened by the mass and U-think entropic bound, which is h of x plus h of p is greater or equal than logarithm of pi e and h bar. And h of x in that case is the Shannon differential of entropy of the probability of the position probability distribution function. And the same is true for h of p. It's the same definition, the momentum probability distribution function. So we have replaced variances now by Shannon entropies. And the ignorance, so to say, that we can have in accuracy is now counted in bits or nats. And when we move now on to this entropy a little more, those logical bits would add up to an entropy density S of x and the conserved entropy current. So entropy is not only bookkeeping, it flows like a heat or charge. And this is the entropic uncertainty principle. Shannon entropy of position plus the entropy of momentum can't be arbitrarily small. So, and the fact that we see in the relation here is that actually very much in Heisenberg's uncertainty, the sum must be at least the logarithm of pi EH bar. And now lastly, I'm moving to the right-hand side here. In anti-de Sitter and conformal field theory, there is the Ryu-Takayanagi formula, which turns this entropy into area. So we now say the area here, the gamma A is the minimal area bulk surface of the region A over 4 times the gravitational constant. And that now allows us to say information sculpts geometry, so to say information gives rise to geometry. And the geometry information duality makes the final arrow local. So whenever there is a flow of entropy, it stresses space-time. So summing up once more, if we say we have the Heisenberg's uncertainty principle that tells us there is a floor to how sharply the nature can or allows us to determine position and momentum in that case. The Maaßen-Hufing inequality rewrites that floor into the h of x plus h of p. So the forbidden region is now measured in information units. And moving one step deeper, Ryu-Takayanagi tells us that those informational units translate directly into a geometric area in the bulk of the ADS CFT spacetime. And put together, we have this three-link system now. The quantum uncertainty leads to entropy, leads to geometric area. And then we take the final leap, and the final leap is if entropy already sets static areas, then a flowing entropy current should act as a dynamic source of curvature. And that is the piece that we encode in the stress energy tensor, in this informational stress energy tensor mentioned at the beginning, that we add to Einstein's equations. And moving on to this one here, very briefly giving an overview of this informational stress energy tensor, we have two components. We have a dynamic pressure component and a quantum pressure component for the entropy forecurrent, which is J upper S sub mu. And the dynamic pressure term, if we start out with that one, acts like a perfect fluid. We assume an equation of state, which is one. An equation of state, one means we have a stiff fluid, and that develops a shear when entropy flows. And the second term, the quantum pressure, penalizes these sharp entropy gradients. That's a potential that keeps us from forming cusps. And that means by construction, we encapsulate all possible entropy-dependent corrections that we have in a gravitational action without introducing any derivatives or higher order than two. And thereby we ensure that the field equations remain well posed. Then posing the covariance then guarantees us that the resulting stress energy tensor transforms correctly under coordinate change, while the divergence-free condition ensures that the conservation of energy and momentum is given. So these two dimensionless parameters that we see, by the way, the lambda and the beta here, are the stiffness, which controls the strong gradients or how strongly gradients of entropy contribute to the classical pressure-like stress. And beta is the quantum pressure parameter, which weights the second derivative of the entropy. Now, the last part is how we modify the field equations. The general introduction here follows after the ordinary matter. So we see two components here. The one I'm talking about today is just the informational stress energy tensor. There's another one on the right-hand side, the uncertainty back reaction. This is a publication that we currently have in review, so that is not out. It's just a preprint, but not reviewed. So I added it just for completeness since this is our last thing that we added. So on the left-hand side in the equation, we see the standard Einstein tensor with a cosmological constant, and on the right-hand side, we see the ordinary stress matter tensor plus these new sources. And that leads us to a running of Newton's constant. So if we project the equation onto momentum space and do tensors make Newton's constant run logarithmically. So depending on the regime, depending on the entanglement properties of space-time, we see different effects of Newton's constant. Now, if we look at the potential experiments and what would we expect in the future, so this is not yet something that's done. This is just a graphic that I created with code. But if we look at the left-hand side, in pure general relativity, you would have the photons orbit the Schwarzschild black hole at the radius of 3 over c squared, which appears as this familiar dashed photon ring in the image. And in gravitational, geometry information duality, the informational stress energy tensor adds a small self-force. And this one leads to shifts in photon orbit. This can be calculated. It's very small, so it's at the order of 10 to the minus 3. But then, as we mentioned briefly before, with the next generation Event Horizon telescope, it should be possible to resolve this and should be possible to detect if that is a true assumption. Other things that we can look for are gravitational wave dispersion. So when we look at the figure that we see here, then the solid cyan is the general relativity prediction. And again, it's a more cartoonish one that I created, but it's based on data, so it should give us an indication as to what real data should look like. And the dashed red one is the prediction, including the general geometry information duality with a small negative contribution by the information that we expect to cause curvature. So we'll see if the experiments lead to success here. We can also do tabletop experiments. So for example, try to find out about the torsion balance, see that the informational pressure adds a tiny torque, and that can be measured, for example, by optomechanical instruments and other experiments the like. And we have not done any of these experiments. So what we currently have done was write out the theory, the hypothesis, but potentially looking forward to collaborating or bringing these experiments to life with other folks. So furthermore, if we look at the theoretical landscape, this is another more advanced work that we currently put out. The original one was a formulation of the informational stress energy tensor. Also here, I'm cautious because this is a preprint and currently under review as well. But one of the questions that we got from reviewers when we published the first one was about renormalization group flow. And of course, we had to address that. And what we found out is that geometry information duality is asymptotically safe, and couplings stay finite to the Planck scale. We also calculated the running couplings that we can show here briefly in the chart. That's more detail in the publication that we have out. But if we look at the turquoise one, it stays flat until the entropy sector becomes dynamical around 1 electron volt and then falls logarithmically. The additional one in yellow gives us dips and a sharp cusp at 1 electron volt and then rises. The reason for that is as we see a sign change at that scale, and we plotted the absolute value here. So the zero crossing shows up as a V before the quadratic growth dominates. And lastly, the gray one is the informational coupling, which first dips because of the beta function turns negative at the entropy threshold. But then the minimum is the sweet spot that links the physics, hopefully, to horizon thermodynamics. So the takeaway from that one is that below a few electron volt gravity is practically classical, but then once information flow is resolved, the three couplings fan out in distinct directions. And that is exactly what we hope that we will be able to measure and probe with the next generation Event Horizon Telescope, LISA or torsion balances. Um, Moving forward, we have a couple of other interesting directions. So the diagram we see is a tensor network with honeycomb tensors here. And each boundary layer, or the boundary layer, so the outer ring here, where you see each leg is an ordinary qubit. So if we move on to quantum computing and data, you could store on the quantum computer. Interestingly, we had an experiment where we took this measure, so this information measure, and we're thinking of how would a retrieval and imprint mechanism in space-time work. So how is this information actually written? And that we could probe using a quantum computer. So we simulated that imprint mechanism and the retrieval mechanism also in noisy conditions. And that besides showing that with high fidelities, we can read out this information. We could also show that this is a valid error correction code. So this has direct implications now for quantum computing. And in my primary work life, so to say, I work at a quantum technology company where we do quantum computing, and that we now integrate into our algorithmic software, and that allows us to reduce the number of qubits, physical qubits, by about 35% per algorithm. It doesn't matter which algorithm, it just cancels out or basically mitigates the error that we see in uh, using quantum computers for hybrid quantum algorithms. We had this one before, so I will now skip and go on to the outlook. These are the experiments and the tests that we expect to see. So the next generation Event Horizon Telescope. So we should be able to go into micro arc second regimes and imaging Sagittarius A star and also Messier 87 star, and should be able to detect, for example, the photon ring changes if we see the theory becoming true or being true. LISA is also very interesting, and sub-millimeter torsion balance upgrade, which we briefly discussed before, and a couple more experiments that we can do. It is not resolved, so the theory is still very much in the working. We have many open questions. The most important ones could be back to the two parameters we briefly discussed of the pressure. So can we derive them from a string bit or a loop quantum gravity microstate count? I think that would be a very interesting question to ask. The second question regarding dark sector screening, does hidden sector entropy shield visible curvature the way chameleon fields screen fifth forces, for example? So that's a very interesting research direction in our view. And lastly, in terms of universality, do neutrinos also, with their huge cosmic background entropy, couple differently to geometry than baryons? So that's a question we haven't asked yet, but I think would be very interesting to ask. Generally, I will conclude now after my 30-minute slide here. And the key message that I hope I could transport today, so based on this work that we put out there, is that geometry is not merely the stage on which information plays. It may be actually information itself. And I know this is a very big research area for your teams, your groups as well. So I'm not telling anything new here. Thank you very much for listening, and hope we have some interesting conversation for now.